Alright, this is Jack Jackson back again. We're looking at probability statistics and inferential statistics. And we're in the middle of trying to develop a technique for deriving what's called a confidence interval. So this video is 4.3.2. We're looking at a one sample z-interval estimate for population mean. So we want to find the upper limit of a standard normal curve by standardizing the upper limit on the distribution of x values. So the upper limit that we're looking at for this part of a standard normal curve here is what we call z alpha over 2. So alpha over 2 is this unshaded area to the right. So 1 minus alpha over 2 is the area to the left of that. And remember, when you were doing an inverse norm, say in our calculator, it always asks for an area to the left. So this would be, in the calculator speak, it would be inverse norm of 1 minus alpha over 2. I kind of wish they didn't give an area to the right here and left here. I wish it was just always left, but this is the way the notation is. The subscript here always refers to what's to the right, and what's inside here always refers to what's to the left in terms of this probability or shaded area under the PDF. Well, actually not just the shaded area. The shaded area here is 1 minus alpha, but you add an alpha over 2 here, and this makes 1 minus alpha over 2 for this, and alpha over 2 for the unshaded area on the right. So anyway, we find that inverse norm, and that's going to give us this value right here, and that needs to correspond to a z-score. Well, that z is mu plus e minus mu over sigma of the x bars. In other words, that's just e over the sigma of the x bars. So we basically have this setup that we have inverse norm of 1 minus alpha over 2 is e over sigma of x's. So that's going to be an important relationship. So we have e over sigma of x's is what we call z alpha over 2, or inverse norm of 1 minus alpha over 2. Now we're assuming that we know sigma, the sigma of the x's. So we're going to replace the sigma of the x bars by sigma of the x's over square root of n. And so now we have this formula right here, which we can solve for e. And that e is sigma of the x's divided by square root of n times the inverse norm of 1 minus alpha over 2. And what this formula allows us to do is to first establish the 1 minus, well, if we actually first establish a confidence level 1 minus alpha, solve that for around until you get 1 minus alpha over 2. So then you know what to put in here. And the sigma is assumed to be known. And if we know the sample size, we can plug that in. And this allows us to find the margin of error. So let's put this formula into work for a z-interval setup that we discussed in the last video. So if you remember, our example from the last video is, suppose that we're interested in knowing the mean weight of all 7th grade boys in the United States. So again, remember, it was impossible to measure all of them, so instead we measure the weights of a sample of n equals 36 boys, and let's suppose that we found the mean weight for the sample to be x bar is 100 pounds. And we know this is the best point estimator, but what we want to do is use this to develop a confidence interval estimate. And furthermore, let's say that we know from past history somehow that the standard deviation of the population of individual boys' weights in this category are 12 pounds. So we record the known standard deviation. Sigma of x is 12. That's the standard deviation for the individuals. We collect some data and measure its sample mean. In this case, the data was collected, the mean is measured and given to us as x bar is 100. That's the sample mean. And then we record the sample size, n equals 36. So now we have those three numbers. Now we need to establish a level of confidence, and earlier in our last video we decided we're going to use 95%. So 1 minus alpha is 95%, or 0.95, and so alpha then is 1 minus that, which is 0.05. That makes alpha over 2 0.025, and then 1 minus alpha over 2 0.975. So notice that little sequence of events where we go from 1 minus alpha to alpha over 2 to 1 minus alpha over 2. We're going to need to do that a lot. Okay, so we have 1 minus alpha over 2 is 0.975. Now, in our last video, we derived this formula. E is the sigma of the x's over square root of n times inverse norm of 1 minus alpha over 2. In fact, we actually just talked about that earlier in this video. So we can now compute the margin of error because everything on the right side we can plug in. The sigma of the x's is just 12. We know that. We know the sample size is 36, which you work that out. 12 divided by square root of 36 is 2, which is just the standard deviation of the x bars. So that's what's in the parentheses here is 2. And the 1 minus alpha over 2 is 0.975. So this is just 2 times the inverse norm of 0.975, or here you see it worked out here. And I stored that as E, and that turns out to be approximately 3.919927972. And then our interval then is just x bar minus E to x bar plus E. So we do 100 plus E and 100 minus E, and that gives us our confidence interval here from, on the left side, 96.08007203 to 103.919928, and here I rounded off to hundredths place, so that's 96.08 to 103.92. So what does this mean? It means we're 95% confident that this interval contains the true mean. Do we know the true mean? No, that's the whole point. We don't know the true mean of the individual boys' weights for the whole United States. We do know the average for our particular sample, which is 100, which is exactly smack dab in the middle, in the midpoint of this interval. But we can go to the right and left of that about 3.92 units. That 3.92 is called our margin of error. The 100 is called our x bar, and then this is our confidence interval. Now let me illustrate that. So going back to the original curve, now if we assume that, unknown to the researchers, that the true mean is 101 and the true standard deviation of the x bars is 2, then we have graphed here the distribution of the sample means, the distribution of the x bars. And notice we developed in the last video, this red area is our confidence level, is 0.95, which is our confidence level. And then we have this interval of width E that's centered up at the true mean of 101, and that goes from, well, about 97.1 to 105, and we have that interval there. The confidence interval is an interval, this blue interval down here, that has the same width as this red region, but it's not centered the same place. So notice it's centered up at 100, which is, say, maybe about here, and we go E to the right to 103.91 or 103.9, and to the left at 96.1, and we have this confidence interval. And notice in this case, the true mean is right here. It actually is in the interval. So again, if you think about playing a game of darts, we miss the mean with the tip of the dart, but if we allow our wings to spread out here, we are going to capture this this particular thing. Or think about this: put a little X on the put a little vertical line on the wall. Stand back, look at it, close your eyes, walk up. Can you hit that line exactly with your nose? Maybe kind of hard. Now that would be like a point estimator. But on the other hand, say maybe spread your arms out and walk up there. Now even though your nose might land on it, somewhere between finger and fingertip, there's a good chance that you're going to actually catch that line that we're looking for. And so that's basically the idea of what we're trying to do with the confidence interval. So the confidence interval, again, is this blue interval here. We don't really know where the actual value is up here. Now, be sure that you understand this, because it's a lot of people make a mistake in interpreting this a little bit. So when you do this computation, we don't know the population mean, but that doesn't mean it doesn't have one. It's got one. In fact, it's constant. There is some mean of the population. You just don't know what it is. Okay? But what's variable is the x bar. If we take a sample, we get one x bar. We take another sample and measure, we get another x bar. Take another sample, we get another x bar. Now, if we decide to keep the E and the N the same from sample to sample, then the only thing that's varying is the x bar, which means the widths of our intervals are staying the same. It's the center of the interval that's varying. Now, if this process is repeated over and over and over and over again, we're going to get a whole bunch of these different confidence intervals. And when we say that it's a 95% confidence, what we're saying is that on average, about 95% of those confidence intervals should actually contain the true mean, unknown to us what it is, but it's going to contain it. So 95% is 19/20ths in a fraction form. So that means that if we do this, about 19 times out of 20, the mean, the confidence interval is going to capture the actual mean. Or we could say that means about 95% of the time the mean is in the confidence interval. But remember, it's not saying that the mean is moving around and it's going to land in there 95% of the time. No, the mean is not moving. It's the confidence intervals that are moving around. So that's illustrated in this picture on the right here, where you can see the true mean of 101. You can see where it is. And I have 20 confidence intervals. 19 of them actually contain the true mean. And the one that's in red does not contain the true mean. All of those confidence intervals, the red ones and the blue ones, are the same width. And they're also the same width as that red region up above. But the centers of them are moving around. Okay. Let's take a look at another important idea. And notice that this formula that we have here at the bottom of the screen, E equals sigma of x over square root of n times inverse norm of 1 minus alpha over 2. Now, right now, we're assuming the sigma of x is something that we actually know. It's a constant, and it's a known one. So that's going to be a number we're going to actually plug in. So then we have variables of things that we can maybe control or have some effect on or choice on. One is the sample size n, right here, under the square root right here. Another one is the confidence level 1 minus alpha, which is in turn going to determine this value 1 minus alpha over 2. And the other one is the margin of error E, which is going to determine the width of our interval. Now, what do we want to have happen? We would like to have a high confidence level. You know, if we got a interval estimate, but it was only 10% chance that it contained the true mean, that's not very very useful, right? Or if we have, we may have we also want a low margin of error, right? So we could maybe have a really wide margin of error and have a very high confidence, but you know, that margin of error, maybe it was a couple hundred units wide. That maybe doesn't narrow down where the true mean is very much. On the other hand, we would like to have a low sample size. It costs money to go out and actually, money and time to go out and actually do a larger sample and measure it. So we keep our cost of our survey and our study down if we can keep the sample size a little smaller. So these three things in this formula are basically in a three-way tug-of-war. And unfortunately, they pull against each other. They work opposite from the way we'd like them to work. So, for example, if we fix the sample size, then you've got a two-way tug-of-war between confidence level and margin of error. The higher you make the confidence level, the higher you make the margin of error, and vice versa. The lower you make the margin of error, the lower you're going to make the confidence level. So you have to reach some sort of balance between those two things, right? Or if we fix the confidence level, then you've got a two-way tug-of-war between the sample size and margin of error. So a low margin of error is going to force us to have a lower margin of error is going to force us to have a higher sample size. It's going the wrong direction there, right? And a lower sample size, we can get that but that's going to make the margin of error larger. So what we often do with this is we actually will decide ahead of time on a confidence level and margin of error, and then solve for the sample size. And I'll show you an example of that here in just a minute. So the whole point of this, though, is to balance these things and avoid extremes. So we can get a very high confidence level, but it required unreasonably large margin of error. So for ridiculous extreme, let's look at this example. We can be 100% confident to capture the mean if we take an infinitely big margin of error, but that's useless to say, oh, well, the mean is somewhere between negative infinity and infinity. Doesn't really help a whole lot. We're 100% sure it's true, but not very helpful because the margin of error is too big. Okay. On the other hand, we could get a very low margin of error, but this might require an unreasonably low confidence level. So we might have a margin of error very, very small, like 0.001%. But this might require a confidence level that's really small, like say 5% or something like that. But again, that's useless because if we're only 5% sure that the interval contains the mean, we still really don't have an idea where the mean is. So what we usually want to do is establish a confidence level and a margin of error that we can live with, and then use that to solve for a reasonable sample size. So we'd like to keep the cost of studies down by keeping the sample size lower, but what we usually do is try to find the sample size that we will need. So, so here are the basic formulas. What's really the same formula? The formula is E equals Z sub alpha over 2, or that's also known as Z alpha over 2, remember, is inverse norm of 1 minus alpha over 2, times sigma of x over square root of n. If we solve this for, let's solve for E, we could solve it for the alpha or the Z alpha over 2. We could also solve for n. So we're going to solve it for n this time. So what I'm going to do first is multiply both sides of the equation by square root of n. Then I'm going to divide both sides of the equation by e. And then I'm going to square both sides. And then I've got a formula to solve for n. The way you'll see it in most textbooks is the first way. N equals Z sub alpha over 2, sigma of the x's of the individuals divided by e, and then square it. Or the way you would do it in your calculator, of course, is Z alpha over 2 is really actually inverse norm of 1 minus alpha over 2. So we might write it the second way. N equals, parentheses, inverse norm of 1 minus alpha over 2 times sigma of x's divided by e, and then square it. In the TI-84 notation, here are the formulas solved for each of the variables. The one in the middle is the one we started with. E is sigma of x's divided by square root of n times inverse norm of 1 minus alpha over 2. The one that we just solved was for n, which is inverse norm of 1 minus alpha over 2 times sigma of x's divided by e, and then square the whole thing. We can also take the same thing and solve for, like say, take the middle version and solve for 1 minus alpha. And it turns out that 1 minus alpha is the probability that that you go from x bar minus e to x bar plus e with a mean of x bar and a standard deviation of sigma of x's over square root of n. That's one way to get that, and that will give you, use a normal CDF to get that probability. That probability is our confidence level 1 minus alpha. And that's essentially 3 different versions of the same formula. The last one is solved for n, the middle one is solved for e, and the first one is solved for 1 minus alpha. We use the first one if we establish a level of confidence and a sample size, if we establish a margin of error and a sample size up front, we could use that one to solve for the margin, or for the confidence level, excuse me. And we use the second one most often. We're going to use the second one where we know the confidence level, so we can figure out 1 minus alpha over 2, do the inverse norm of that, and we can use the other parts of that one where we know the sample size to find the e, and that's going to allow us to help us build our confidence interval, which is just mu minus e to mu, x bar minus e to x bar plus e. So we normally use the second one to actually build the confidence interval, but what you do in practice before you go out and actually collect your data, you want to make sure you got an adequate sample size, and so you would do the formula on the last one where you sort of decided what level of confidence and margin of error that you're willing to expect. Okay, so we're going to put this to work in some examples here, a couple videos down the road, but the next video, before we do that, we're just going to briefly review some things about the normal probability distributions and sampling distributions to make sure we've got all those skills brushed up and ready to go for our computations later on, because we need to make sure we understand things like normal CDF and inverse norm, that we know how to compute those things and what they mean and how we can visualize those. So we'll pick up with that quick review in the next video.